So first of all, I would like to say I'm really happy to be in Buenos Aires. I've always wanted to come to Ekoparty. And yeah, I never imagined I'll be a speaker the first time I'm actually here. So yeah, I really love this conference. I'm a security researcher for MWR in the UK. I break various stuff, but I mostly focus on network protocols, reverse engineering, bug hunting in general. So today I'm going to talk about MPLS networks, how to pen test MPLS networks. What is MPLS? MPLS is a mechanism used in high-performance service provider telecommunications network that allows for transport of data from point A to point B, where the forwarding process takes place on layer 2, or strictly speaking, layer 2.5. And instead of having forwarding decisions on a hop-by-hop basis, decisions are made based on labels that are assigned based on what is called LSP, or label switch path. So why is MPLS being used? Well, because this sort of forwarding based on labels is a lot less expensive for the processor because the MPLS header is a lot more simplified compared to the IP header. Because of the fixed size of the MPLS header and the less complicated process of performing a lookup on a label as opposed to performing a longest prefix match on a destination IP address, MPLS is the preferred technology in high-performance networks. So as I said, single longest prefix match and then lookup in what is called label information base, which is basically a routing table sort of for MPLS, where IP addresses correspond to labels. Service providers use MPLS as an underlying technology to actually build layer 3 and layer 2 VPN solutions on top of it. Now, a bit of boring stuff, but I need to mention some of these things before I move on. As I said, labels are basically the heart, the core of the protocol. These are 22 bits, 20 bits integers. There's 3 operations that you can perform on a label: pushing a label on a stack, popping a label off the stack, and swapping labels. There is reserved labels from 0 to 16. These are various labels defined for administrative purposes, and they have some special meaning. I'll be probably mentioning some of the reserved labels a little bit later. So a router that actually performs label switching is called a label switching router, or just LSR. Strictly speaking, an LSR is a provider router, what is called a provider router, or router that sits somewhere in the core of the MPLS backbone. A label edge router is a router facing a customer device. So basically, at the edge of the MPLS domain, you have a provider edge device, and on the side of the client, you have a client-side customer edge device. And this is where the customer connects to the service provider, the MPLS service provider. So from customer side A to customer side B, the logical path from side A to side B is called label switch path. An important thing to understand is what VRF is. So VRF stands for Virtual Routing and Forwarding. If you're familiar with VLANs, you can think about VRF as a VLAN on layer 3, as opposed to a classic VLAN on layer 2. So VRFs allow for having sort of virtualized instances of a router within the router itself. So basically, you have a number of instances of a routing table. There are some tricky things about VRFs. So for example, you may have overlapping address spaces in these VRFs. You may leak routes from one VRF into another VRF. You can leak routes from the global routing table into a VRF or from a VRF into the global routing table. But yeah, for the purpose of this talk, just imagine VLAN segregates a network on layer 2, and VRFs allow for segregating a network on layer 3. Now, this is the most basic example of what an MPLS network would look like. You have the customer edge device, which is basically where the customer network ends and connects to the provider, connecting to the provider edge device, or the PE. Then the core backbone of the network is basically what they call provider routers, or just P devices. And on the other side, you have the exactly same scheme. So customer side A and customer side B, they should take this MPLS network as a transparent thing. Basically, when you send traffic from customer side A to customer side B, you shouldn't care about the MPLS configuration of the service provider network. It should be fully transparent. Now, talking about where the customer network ends and where the service provider network starts, we also need to understand what is the process of handling traffic at the edge of the MPLS domain. At the edge of the MPLS domain, the provider edge device performs a lookup in the label information base in order to assign a label to a particular traffic. Now, in this label information base, you have destination networks and corresponding labels. At the edge of the network, when a label is determined for this traffic, an MPLS header is inserted within the Ethernet header and the IP header. And that's why MPLS is sometimes referred to as layer 2.5 traffic. It's also good to know that you can have multiple MPLS headers. So basically, you can have a series of labels, and these series of labels are what is called the label stack. This is how the MPLS header look like. The important bits of this header are the label field and the TTL field. The experimental field, as far as I know, is not being used at the moment, and the bottom of the label stack is a 1-bit field that basically tells you, is this the bottom of the label stack in case there's multiple labels assigned to this packet. Some previous MPLS research, security-related research, focuses on mostly assumptions about an attacker being able to, for example, access a network. Not just access a network, but having exposure to the backbone of the service provider. And from the perspective of an internal attacker, people have been looking at various scenarios about injecting traffic into different VRFs or redirecting traffic from one VRF to another VRF. Another assumption is that a provider edge device, as stated in the RFC, should never process MPLS encapsulated traffic when it is received from a customer. This means a customer should only send clear IP traffic to the provider, and in case a customer decides to encapsulate traffic in MPLS, or due to misconfiguration, encapsulates its traffic in MPLS, the service provider should just discard this traffic and should not process this traffic any further than that. Again, this seems to be true, as stated by Enno Ray from ER&W, really good piece of research, and apparently they tested Cisco kits for this kind of attacks. Now, I want to start with really basic network reconnaissance. If you remember, there is a direct link between a customer and a service provider, basically the CE link and the PE link. Now, from this perspective, a client can do some really basic reconnaissance and check the MAC address of the device on the other side of the link and derive the vendor from this MAC address. A customer, an attacker in this case, can check for the presence of link layer, discovery protocol frames, CDP frames, or MNDP frames. These are layer 2 management protocols used for advertising various kind of metadata about the device. So, for example, which is the vendor, what is the remote interface, what is the MAC address, what is a VLAN in case this is on a VLAN, etc., etc. So basically leaking a lot of extra information. And these protocols, of course, should not be enabled on a customer-facing interface. But due to misconfiguration, you may be able to spot some of these. Another one is misconfigured routing protocols. So, for example, OSPF hello packets sent on a customer interface, or IS packets sent on a customer interface where this should not happen. Again, this can reveal some specifics about the vendor, the vendor's device that you are facing directly. And in worst case scenario, there may be some services enabled on the service provider side device, on the PE device, like Telnet, SSH, HTTP, etc., etc. Well, this is really rare, but this is the most basic things that you're looking for when you start, when you perform reconnaissance on the service provider network. Now, there is this interesting RFC called Analysis of the Security of BGP MPLS IP VPN Networks. And this basically tells us that it's a best practice to hide the MPLS infrastructure from the client. As I said, the MPLS domain should be fully transparent, and from a customer perspective, there should be no information leaked about this MPLS domain. Basically, this means that a customer should have no idea about the number of devices along the LSP, should have no idea about the labels being used within the MPLS domain, should have no idea about the IP addresses of these LSR devices. And how is this being achieved? There's two basic mechanisms, two basic security mechanisms. One of them is IPTTL propagation. Another one is called ICMP tunneling. If you remember the structure of the MPLS header, there was a TTL field. Now, the role of the TTL field in an MPLS header is exactly the same as the role of the TTL field in the IP header. So what is IPTTL propagation? Well, this is the process of a provider edge device taking an IP packet from a customer, parsing the packet, the IP header, taking the TTL, decrementing it by 1, and using this as the value for the TTL in the MPLS header. Basically, propagating the TTL value from the IP header in the MPLS header. Why is this a bad thing? Well, because using traceroute, an attacker may be able to kind of reveal the number of LSR devices in the network. In certain cases, their IP addresses. Propagating the TTL is enabled by default, and the security best practice is to disable this thing. ICMP tunneling is another mechanism related to how ICMP error messages are handled within the MPLS domain. So imagine, let me see if I have a diagram for that. Okay. Imagine from client side A, I sent ICMP EC requests to the far end of the VRF to client side B, and there's IPTTL propagation enabled. So if there's IPTTL propagation enabled, I should be able to generate ICMP error messages at the provider edge device, the provider core device, and the far end provider edge device. If I generate these messages because of an expired TTL, these devices should have a mechanism for returning the ICMP error message back to back to the originator, in this case, client side A. The problem with MPLS is the core devices are just dumb devices. They have no idea about the VRFs. The only devices that have VRF relevant configuration are the provider edge devices. So if there is an ICMP error message generated in the MPLS core network, the stupid device would have no idea how to handle this traffic, because this traffic should be sent back to myself. Now, instead of just discarding this, when ICMP tunneling is enabled, the ICMP message will travel all the way to the far end of the VRF before it leaves the service provider network, because this device will have the relevant VRF configuration. And because of having the relevant VRF configuration, it would know how to send traffic back to myself. It will label the traffic and send the error messages all the way back to me. So this is the ICMP tunneling. Okay, when you have IPTTL propagation enabled and ICMP tunneling enabled, TTL propagation needs to be enabled at the edge of the network, and ICMP tunneling needs to be enabled all along the whole LSP, basically needs to be enabled on all of these devices. When you have these two mechanisms basically enabled, TTL propagation needs to be enabled and ICMP tunneling needs to be, yes, when you have them enabled, you should be able to not just reveal the number of intermediate devices from customer side A to customer side B, but you should also be able to leak internal IP addresses and some information about the labels being used for labeling traffic within the MPLS domain. Again, this information is only available to an attacker when the service provider does not follow the security best practices. And in this talk, I consider a scenario where the MPLS network is configured according to best practices, TTL propagation is disabled at the edge of the network, and ICMP tunneling is disabled along the LSP. So basically, no way for us to generate ICMP error messages and get them back. The most basic question we can ask and start with is related to the number of devices between us, between one customer side A and customer side B. Why is this interesting? We'll see in a minute. But there's a really basic technique that can actually tell us how many service provider devices are between one of our sites and the other, and the far end of this site. And this technique is basically around crafting packets, ICMP ECK requests in this case, encapsulating them in MPLS before sending them to the service provider network, and increment the TTL values in the MPLS header, not the TTL values in the IP header. The label that we use for the MPLS encapsulated traffic may vary according to vendors, per vendors. In most of the cases, I found that this is only possible when you set the label to be 0. And as I said, 0 to 16, these are reserved labels. Prerequisite for this attack to work is to have the PE device processing MPLS encapsulated traffic from the customer. So this is the way we craft these devices, craft these packets. I use KP for all of my tests. KP is definitely the best packet crafting framework I've ever seen. You need to load the MPLS module because it's not loaded by default. It's considered to be in a beta state or something. So you need to load the MPLS module. You need to configure, to basically set your source and destination MAC addresses, stick an MPLS label on top of internet, and then in the IP header, point to the far end of the VRF that you're into, and of course, append some ICMP. By default, this is ICMP echo request, I believe. So this would generate 4 packets. Why 4? Because of the TTL range set from 0 to 4. The result of this is roughly described in this packet capture, basically. The reason I only have a packet capture for this attack is because I have only performed this in production network, and I didn't manage to reproduce it in my lab. So in production network, I was facing some vendor devices that I was not able to test in a virtualized environment. So basically, you can see for the first MPLS encapsulated ICMP echo request using TTL 0, we get an ICMP time exceeded in transit error message returned back to us. Incrementing the TTL by 1 gives us back the same error message. Incrementing again gives us back the same message. Incrementing to 3 basically results in silence. There is no response. So this tells us something about the number of intermediate devices from customer side A to customer side B. Now, having an idea about the number of devices is not really exciting, but it is a good start. Now, let's find a way to actually get some sort of IP addresses used within the MPLS domain. Again, remember IPTTL propagation is disabled, and ICMP tunneling is disabled, which basically means when we perform a trace route, imagine this VRF A customer face, service provider facing customer device. It's just a Linux box. When we perform trace route across the LSP to the far end of the VRF, we cannot reveal any information related to the service provider network. The only thing we see is our default gateway IP address and the remote IP address of the far end customer edge device. And here's some magic. So basically, if we send an ICMP echo request to the far end of the VRF, but using what is called IP record route, something that most of the people know about, we can get a response back. In this response, we have 2 IP addresses that I haven't seen before. And I wonder, what are these addresses? Now, when we look at the network, we see that we get 172.16.0.6 and 172.16.0.1. Now, IP options, the record route IP option works roughly like this. So basically, we send our message across to the far end of the VRF. This device will reply with an ICMP echo reply, and we'll use the same IP options that we use for the echo request. When this device handles the traffic, it parses the IP header, sees that there's IP options enabled, the record route IP option is enabled, and puts the IP address of the egress interface into the list of IP addresses of the IP option in the IP options field. Same applies to this provider edge device. So basically, when a packet comes from customer side B to customer side A, on the way, we'll be able to reveal the IP addresses for the egress interfaces. Now, the interesting thing about this is why the heck LSR devices. Shut up! Why the heck LSR devices actually consider, oh no! Okay, that's a good time. So remember, the good thing about the good thing about forwarding MPLS traffic is that it's efficient. It takes a lot less CPU time to process the MPLS header. Now, cheers. One more. The interesting thing is, why the heck this MPLS-enabled device even looks at the IP header? I mean, when I discovered this problem, I sent an email to the affected vendor, one of the affected vendors, and I asked them, do you think there is a misconfiguration in my network? Because the way MPLS works is, well, basically, we only care about the label. We don't care about the IP header. Not even talking about the IP options field in the IP header. So I asked them, do you think there is a misconfiguration in my scenario? Because this thing is absolutely nuts. This shouldn't work like this. So they looked at it. They reproduced the issue in their network, and they said, wow, well, I don't know. I have no idea why is this happening. And I'm like, OK, if you don't have an explanation, I guess I don't have an explanation either. So yeah, with just this simple thing, enabling IP options record route, you can reveal, again, certain number of vendors were affected by this. A few vendors were found to be unaffected. But it's a shame. I mean, it just doesn't make any sense at all if you think about it. So now that's the information we have at the moment. We started with nothing. Basically, we started with just the number of intermediate devices. Now we have the IP address of the provider edge device on the far end and the IP address of the provider core device. This is good. And because you would think in an MPLS environment, links between these devices are point-to-point, you can assume a /30 subnet mask and derive the IP addresses on the other interfaces. So basically, in this 172.16.0.0 network, if we have the .1 address, we can assume, safely I would say assume, that the other end of the link is .2, because this is the only other valid IP address. So we got some IP addresses, we got the number of devices. A question to ask is whether we can send traffic to an MPLS-enabled device in the network. I told you that a provider core device would have no idea about how to return traffic back to us. So the sensible thing to do is to send traffic to the provider edge device, but not to the provider edge device customer-facing interface, but the MPLS interface, in this case, .2. And in this case, it works. To be honest, this only worked with 1 out of 5 vendors I tested, but it was a surprise, because not just that you should not be able to reveal the IP addresses, but in any case, you should not be able to send traffic to MPLS-enabled interfaces. In this case, basically, we have PE1, this PE device, having this IP address assigned to its MPLS-enabled interface, and we are able to send traffic directly to it. And the only reason we see the responses back is because this device has the relevant VRF configuration. Again, a serious problem, but only affects a single vendor. What can we conclude from all of this? So basically, one vendor was unaffected. None of these problems was present in one of the vendors' implementation. Several vendors were affected by one or more of these problems, and one vendor was affected by all of these problems. So kind of inconsistent. The question to think about in this case is, what would be the result in a network where you have multiple vendors? Basically, imagine an MPLS domain where you have provider edge device from a certain vendor, and core device from another vendor, another core device from a third vendor, and I don't know, maybe another provider edge device from a fifth vendor. So it's interesting to see what would be the behavior in this case. I didn't test that. So moving on to the more exciting stuff, which is Vref hopping. So far, it was mostly about MPLS reconnaissance. So revealing the internal structure of the service provider network. Something like number of intermediate devices, IP addresses assigned to these devices, etc. If you know about VLANs and VLAN hopping, it's really easy to understand what Vref hopping is. I told you that you can think about VRFs as VLAN equivalents on layer 3. So a Vref hopping is what is the VLAN hopping equivalent on layer 3. This basically allows for being positioned on a certain VLAN and being able to send traffic which destination resides on a different VRF. Why is this a problem? Well, it is a huge problem because service providers often see VRFs as a sort of a security mechanism. They segregate traffic and rely on VRFs to make sure that one customer's traffic doesn't get mixed with another customer's traffic. So the assumption of not being able to break out of the VRF is fundamental to service provider security. Slightly complicated would be the scenario where you have overlapping IP address spaces across the VRFs. I told you that it is possible for various VRFs to have an overlapping address space. But because these are fully isolated, allegedly, this should not be a problem when routing decisions are made. Now, let's start with attacking MPLS clients. This basically means subscribers of the same MPLS network. Customer traffic should only flow within a dedicated VRF. So basically, a customer A should not be able to send traffic to customer B, because customer A is within VRF A and customer B is within VRF B. There is such thing as inter-VRF communication, but this should be explicitly configured by the service provider, and this allows for leaking routing information from one VRF onto another VRF, or from the global routing table into one of the VRFs, or vice versa. Basically, Vref hopping implies that inter-VRF traffic is possible. And successful attack would allow an attacker to, an adversary to send traffic to another customer edge device. And this is the kind of extended scenario that I'm going to use for the Vref hopping attacks. We have customer A, which traffic flows within VRF A. We have customer B, which, whose traffic flows within VRF B. And each of these customers, they have two sites, site A and site B, site 1 and site 2 in this case, sorry. So customer A, we have R1 and R2. Customer B, we have R3 and R4. Okay, let me see. We start with basically, from a customer A perspective, we try to reach customer B device on Vref B. In this case, this is sending ICMP echo request from R1 to R4. As you can see, because we are on different VRFs, our provider edge device would not forward our traffic into the wrong VRF. And that's why we get 100% packet loss. Now, for my demos, I use GNS3, which is basically a front end for something called Dynamips. Dynamips is an emulation framework for creating networks, basically. You can virtualize a whole lot of vendors and interconnect these devices. So in this case, I'm attacking from VRF-A, this VM that you see attached to the provider edge device. I'm attacking the blue VRF R4 device. And this is my VM. Okay, so I run a quick script to just configure my IP address and my default gateway. And in this case, confirming that I have connectivity to my gateway. So I can try and ping the far end of my VRF, which should work. This is basically trying to ping my own device on the other side of the MPLS network. And as we can see, there is no problem with that. Now, when I try to send traffic to a device that resides on a different VRF, we see that there's nothing, basically. Okay. Now, I need to enable ICMP debugging on this remote device. And perform some Vref hopping. Okay, so what you see here is just a wrapper around some SCAPI functions, just to save some time. But basically, let me show you the output from SCAPI. So this is the output from SCAPI. We have the Ethernet setting source MAC address to the VM MAC address, destination MAC address to default gate MAC address. Then we have the MPLS layer setting the TTL to 64 or anything above, in this case, 4 would work. And then setting a label range from 1,000 to 1,500. This will generate 500 packets, 500 ICMP packets. These are basically ICMP echo requests encapsulated with MPLS labels from 1,000 to 1,500. Okay. Shit. God damn it. I knew I need to record these videos. Shit. Oops. No. Fuck's sake. Where's my stupid VM? I need vodka. This is horrific. What? No. Fuck, my VM crashed. This is horrendous. I'm really sorry about that. Back to the presentation. Basically, I generate these packets. If you remember, I enabled ICMP debugging on the R4 device. And on the R4 side, in this case, I see 2 out of 500 packages actually made their way through VRF-A from VRF-A to VRF-B. So basically, we were able to break out of the VRF and send some traffic to a random customer. We are using these label ranges based on some previous research on how different vendors assign labels to different VRFs. So basically, there is a list of vendors and their strategies on assigning labels. Some vendors would start assigning labels from 17. Some of them would start assigning labels from about 1,000. Some of them would start from 2,000, etc., etc. So this is kind of a smart guess. As you can imagine, brute forcing the whole 20-bit range is not that practical. It's possible, but it's not that practical. So if we can shrink the range to about 500 attempts, that's a lot better. So in this case, we managed to get the traffic across the VRF. As we can see, on R4, we see ICMP echo replies sent back to R1. The problem with this is we'll never see the ICMP replies, but more on this in a minute. Now, we see that we are able to send traffic to other customers. We can also try and verify our theory about being able to send traffic to service provider devices. Basically, we know about their IP addresses, we know about the interconnections, so let's try and see if we can actually send traffic to their MPLS-enabled interfaces. In this case, we used the IP address that we were able to leak at the first stage of the attack. We tried to send 3 ICMP echo requests to this P-device MPLS-enabled interface, which is .1. And we see that we don't see anything, basically. We only get a message saying none of these were received on the far end, basically getting a message about the lack of replies. So if we log into the P-device, enable ICMP debugging, enable logging functionality on the terminal that we use, and perform something really similar to what we did for the client attack. But in this case, the only difference is that we use the service provider's internal MPLS IP address instead of the far-end VRFA customer edge device IP address. The MPLS label range remains the same. So we generate 500 packets, and on the P device, we can see that there is an ICMP echo request received, ICMP echo reply generated, ICMP echo request received, and again, reply generated. These replies are generated, but of course, the remote device would have no idea how to send them back to us because there is no route for our IP address that is configured on the P device. As I told you, the P device are really stupid, really dumb. They only follow the labels. They have no idea how to handle traffic back to customers. What is the problem with the Vref hopping attack? Now, the limitations of these attacks are the exactly same limitations we face in a classic VLAN hopping attack, which basically means we can only send traffic one way. We can send traffic to an affected device, but we cannot force the victim device to encapsulate the traffic that is supposedly sent back to us. Imagine when an ICMP echo request arrives at the destination CE, the CE would generate the ICMP echo reply and send it back. Because this traffic is pure IP traffic, it won't be allowed on a different VRF because, well, in case the provider edge device is properly configured. So we need to find a way, basically, to force the remote device to encapsulate traffic into MPLS with a specific label before sending the traffic back to us. Now, this is really hard because we only have one-way communication, and in theory, the only protocol that I can think of that we can attack is SNMP. Another problem is, of course, we have no idea whether this traffic reaches any device at all because of the lack of replies. This is more of a theoretical attack, but I did some tests and I managed to reproduce this. It's highly configuration specific. Imagine you're on an MPLS network, your victim's on the same MPLS network. you need to make the assumption that the remote customer-facing device is enabled for SNMP management. When you have SNMP management, you have read and write permissions. With read permissions, you can query the device for some diagnostic information. With write permissions, in certain cases, you are able to reconfigure the remote device. Again, it's probably time that I mention some service providers, they give you an option of choosing between a managed service and unmanaged service. Managed service means the service provider takes care of your CE configuration. So basically, they give you an already pre-configured device that you just connect to your network and you use. In unmanaged services scenario, you have your CE device. You are in charge of configuring your CE device. They only give you the relevant IP addresses that you need to use for connecting to their infrastructure. And again, this SNMP attack scenario is a lot more likely to succeed in an unmanaged service scenario, because a client is a lot more likely to misconfigure and miss some hardening on its device compared to a service provider. What do we need for this attack to succeed? We need to have SNMP write access enabled on a CE device, something that is, well, again, it happens. We need this service to be accessible on a CE to P link. Basically, we need this service to be accessible on a provider-facing interface. And of course, we need some low complexity SNMP community string or some really smart guesswork. So the attack scenario goes like this. We perform Vref hopping as previously demonstrated, or in this case, not demonstrated. We load a dictionary with SNMP community strings, and in case we have an idea about the remote device vendor, we preload some management information basis for SNMP, extract the object identifiers that correspond to some configuration statements that would allow us to reconfigure this device, and we basically craft traffic as follows. We have the MPLS stuff as in a classic proof of concept, but the only difference is that instead of ICMP, we use UDP with source port and destination port set to 161, and on top of UDP, we stick SNMP. In this case, I said the community string needs to be loaded from a dictionary list, and the SNMP objects that we are modifying needs to be grabbed from a management information base for the specific vendor. The good thing about this is there's some vendor-neutral management information bases, and the object identifiers persist across vendors. So we can remotely reconfigure this device, for example, to configure a static route for this device to point for this destination, to use this default gateway. Another thing that we need to configure is to tell this device to have what is called MPLS static binding rule, which basically means whenever you send traffic to this IP address, the attacker's IP address, you need to encapsulate this traffic using a particular MPLS label. Again, kind of complicated, but I've managed to reproduce it against only one vendor. What are the serious problems related to this? Well, basically, even if you find a vendor-neutral object identifiers that you can modify, these object identifiers vary from versions to versions. And because it's highly likely that you mess something up, this whole attack would result in a denial of service condition, because this far-end device will end up in a misconfigured state, which in most cases results in mishandling traffic for the legitimate other side of the VRF. So a customer would notice that there is something really wrong with this device. A few words on hardening the MPLS environment. As recommended, disabling IPTTL propagation at the edge of the MPLS is the first and major thing to do. Disabling ICMP tunneling throughout the whole label switched path is the second thing to do. As we saw, some vendors are affected by issues that work against the hardened environment. So probably the third recommendation would be to patch your service, patch your devices, or follow the workarounds that will be published by the various vendors. Another thing is to disable the management protocols and unwanted services that run on a customer-facing interface. Basically, cut down the information as much as you can. Enable the GTSM, which is a mechanism that allows for protecting service provider devices against certain denial of service attacks based on the TTL being used in an IP header. So basically, you can make an assumption about the range of your network. If the TTL being processed is outside of the range of this network, of your assumption, you can safely discard a message solely based on the TTL value. And it's probably a good idea to follow the recommendations in the security MPLS RFC. Just some general guidelines. Should always assume the presence of some malicious or compromised clients. Should always restrict the management access to your LSR devices, which basically mean your LSR devices should only be accessible from within the management VRF, and this management VRF should only allow some highly secure, like properly hardened devices to be able to communicate with the LSRs. Secure device management protocols is something that I don't even need to talk about. Routing protocol authentication, of course, enable the highest level of authentication available for your routing protocol, mitigating some replay attacks, etc., etc. MPLS signaling protocols is something that I don't have time to talk about, but MPLS signaling protocols, for example, LDP, is a protocol being used to kind of synchronize the MPLS devices and exchange labels between devices and kind of negotiate the meaning of the labels. Centralized authentication, authorization, and accounting services is something absolutely mandatory. And what I find really important is you need to have a secure baseline, basically having a configuration file that you are absolutely 100% sure is as hardened as possible, and basically replicate this file across the network with the relevant changes, and keep track of every single change you apply to this configuration file. The reason I emphasize on this is because I've been on some tests for customers. They give me 200 configuration files. I looked at them at some easy, fast diffing, and I realized 2 out of 200 devices are really poorly misconfigured, badly misconfigured. All of these 200 devices are internet-facing devices, but only 2 of them are properly misconfigured. For example, having IPv6 peering and not having IPv6 filtering, packet filtering, having SNMP enabled on their IPv6 enabled interfaces, etc., etc. So 2 out of 200. You compromise one of these 2 devices, and then you have access to the whole network, basically, because of stupid things like password-free user stuff. What is a good thing to look at as a follow-up from this research? Well, definitely some ways to improve on the VRF hopping attacks, because at the moment, as I mentioned, same limitations apply that apply to VLAN hopping. It's not as useful as I would like to be. And the only theoretical kind of attack that I can come up with at the moment is compromising a remote CE device using some sort of SNMP. This is blind exploitation over SNMP, and it's not something as practical as I would like to see. MPLS signaling protocols, again mentioned, these are protocols used for distributing label information and basically meaning for these labels. RSVP is another signaling protocol. These are protocols that are basically the core of the MPLS in some way, unless you use statically assigned labels. So these protocols are interesting because for some of them there's an option for remotely establishing a session with an MPLS device over LDP and telling the remote device about some label information that would completely mess with the label information base, for example. Interesting thing to consider is also some fuzzing on MPLS and MPLS related protocols. I would like to thank some guys from MWR Labs South Africa for giving me the opportunity to pen test in a production environment and basically trusting me not to break anything. And I would like to thank my really good friend Pavel, who helped me with basically some setup for these for most of these virtualized devices. Now let me see if I can. God damn it! This is pretty much it, but let me see if I can. Nope, my VM is dead. So, questions?
¿Quién tenía una pregunta?
Hi. So thank you for your talk. Like, it looks like really interesting, mostly because we are seeing more installations of MPLS networks here in Argentina. I would like to know if do you know why in this particular vendor that is looking at and complying with resource record extension, is it on the RFC or is something that they coded? I don't know.
It's an interesting question. I really wanted to know why is this happening, and I didn't get an answer. Basically, they said, we have no idea, we fucked up. This is completely meaningless, and we should not be doing that. And they didn't have an explanation either. Basically, they were like, well, it doesn't make sense, but that's the way it is. So they're fixing it. It must be. Any other questions?
Yes. Oh, yeah.
Sorry about the demos.
Here.
I'll be getting drunk tonight at the bar, and I'll have my laptop. So just come over, and I'll do the demos.
Hi, Mike here.
Oh, okay.
No se ve nada. My question is regarding the VRF Hopping that you did. You are sending the MPLS encapsulated packets to the customer-facing device. So why is it accepting those encapsulated packets? Shouldn't it be dropping it? I mean,
why is not the provider edge device dropping the MPLS encapsulated traffic?
Yes.
Well, that's a good question, and I had the same question for the affected vendors. Is that
a configuration issue? Or?
No. So in case you configure the PE interface to handle MPLS traffic, this attack would work on a misconfigured PE. All of the attacks that I tried to demonstrate, they are on properly configured devices. So basically, it's not a misconfiguration issue. The problem is some of the vendors, when they enable MPLS on certain interface, they enable MPLS globally. So if they receive MPLS on non-MPLS enabled interface, they would still process the MPLS traffic. So it's an implementation issue rather than a configuration issue.
All right. So I have a second question. Your VRF attack, it's like VLAN hopping, but at the same time, what you're doing is sort of like spoofing, because you are sending a label that doesn't belong to that set of IP addresses. Is there a sort of anti-spoofing mechanism either in our RFC or as a configuration option?
So one of the vendors just released an advisory yesterday, I think, and I looked at their workarounds. So if you're not able to patch for some reason, the way to kind of mitigate this attack is to have an access list on the customer-facing interface that specifies in the Ethernet header, there's an ID field. The ID field tells you what's the protocol on top of Ethernet. So is it IP, is it MPLS, is it something else? So their workaround was to have this access list filter traffic for Ethernet traffic with MPLS ID in the Ethernet header. So basically just whenever you see MPLS traffic on a customer-facing interface, just drop it, ignore it. But this is a dirty workaround, applying an access list rather than having a properly designed MPLS implementation.